Okay, welcome back to the Special Functions and Number Theory seminar. Today, we will have part two of Professor Lovejoy's talk on Bailey pairs, radial limits of Q hypergeometric false theta functions, and a conjecture of Ikami. Over to you.
Okay, so let me share my screen. Looks good, I hope. So thank you everyone who came back, and thank you to, oops, I'm at the wrong place. So thank you. Okay. And thanks to those who are watching the second part recorded. So let me review a little bit about what happened last time. So first, I had an internet outage 2 minutes before my talk was scheduled to begin. There was a big snowstorm here, so I have no hard evidence that the two are related, but it's a possibility. And so the internet stayed out for 6 hours. Then I managed to connect via hotspot, which worked for a little while, but turned out ultimately to be unstable. So I had an internet outage, an unstable hotspot connection, and especially a rather distracted speaker. So if you watch the first part of this video, you'll see that I was a bit concerned about my connection. I kept looking at my phone. I probably was racing through my slides trying to get done before my connection cut out again. So let me go over a little bit what happened last time before I get into the second part of this talk. Right, so last time we also had a theorem, and this is it. So this says for any primitive nth root of unity, we have the equality of these two functions here at the bottom. So on the left-hand side, this was or is a Q multisum, which also happens to be a false theta function. And so these values, I'm writing these as values, but these are really radial limits. And then up to a root of unity on the right-hand side, this is equal to a truncated version of this Q multisum evaluated at the same root of unity. All right, so the truncated version turns out to just be a polynomial. So you can evaluate that for any complex number, in particular at this root of unity. So these two are equal. So let me review what these functions are. So the left-hand side, I said, is a Q multisum, which is a false theta function. So this is the Q multisum. Looks like the usual kind of thing we see when we look at Andrews-Gordon type identities or Q multisums in general. This thing might look a little bit different to you. This product of Q binomial coefficients with this delta IA in there. This is becoming more and more common. I'm seeing this more and more often now in families of Q series. Okay, so I said this is a false theta function. This is it. So last time I talked about this little constant m in front. We just kept it there because Ikami put it there for his own convenience. So this is a false theta function. So there's a periodic function here, chi sub 2m superscript a of n. This is its definition. So it's an odd periodic function, which makes this a false theta function. And so it has well-defined radial limits at roots of unity. Okay, so that's what I said there. And then the truncated version is just the truncated version. So this is the same function here. Go back up. So we forget about the constant and this power of Q in front, and we just take this Q multisum and just truncate it. So instead of summing over all ni, we sum up to capital N minus 1. Okay, so the truncated version is the truncated version. And this is just a polynomial. So we can evaluate this at any complex number, and in particular at roots of unity. Okay, Hikami proved his result for little a equals 0 and capital M equals 1 using knot invariance. So he showed that the left-hand side can be obtained by computing the Kashayev invariant for certain torus links in one way, and the right-hand side is obtained by computing the same Kashayev invariant in a different way. All right, so I left out all those details, and I will do so today as well. And he left the general case as a conjecture. Okay, and we proved this. This is a theorem I just put up in joint work with Rishabh Sharma to appear in the Kyushu Journal of Mathematics. Okay, and our proof used Bailey pairs. So I went over this last time. And the point I wanted to make, which I hope I made, is that everything, when you use Bailey pairs, everything works easily, naturally, perfectly, whatever nice adverb you want to put in there. Basically, the first thing you try using Bailey pairs, you try to construct the truncated series using Bailey pairs up to roots of unity. You can, using standard Bailey pairs and standard Bailey pair methods. and what you get is exactly what you want. Okay, but it turns out then that there are other similar results for other Q hypergeometric false theta functions constructed using Bailey pairs, and that's what I want to talk about in the second half of the talk. So let me talk about the steps in proving this, and this will serve as a review of the proof of Hikami's conjecture as well. Okay, so step one is we have a Q hypergeometric multisum, and we prove that it's a false theta function using Bailey pairs. This is not the hard part. None of the parts. Nothing is hard, actually. And then we use classical formulas to find an expression for the limiting values at roots of unity. So once we know we have a false theta function, we can talk about it at roots of unity in terms of radial limits. I'll talk about that shortly, how to use these classical formulas. And then using the Bailey pairs again, in fact, using the same Bailey pair we used in step one, we prove an identity involving the truncated multisum. So we don't obtain exactly the truncated multisum. I talked about this last time. We obtain the truncated multisum up to some terms that have Q to the capital N in them. But if Q is a primitive capital Nth root of unity, this just disappears. Okay, and then we compare this identity with the values of roots of unity in step two. And they're just a short calculation away. Okay, so let me do this in detail for one example, and then I'll just state the other two we did. Okay, so psi sub m tilde, so kind of following Hikami's notation here with the tildes and the Greek letters and the constant in front. This is a 2m minus 1 over 2 times the power of q, and then here's a q multisum. Okay, and the reason that I'm choosing this is because it is a false theta function. Because of this term here, we want to truncate this at capital N minus 1 later and evaluate at roots of unity, but I also want to avoid poles coming from this denominator, so I'll restrict to odd roots of unity throughout. Okay, so the step one, if you recall, is to prove that this is a false theta function. This is a standard calculation using Bailey pairs. I believe I probably said this last time. This is a Bailey pair that just arises from the unit Bailey pair iterated in a standard way. And if you put this into the Bailey lemma in a standard way, you get this identity. So this C sub m of q is this false theta function. So chi sub 4m minus 2 of k is an odd periodic function, has a definition. It's just plus or minus 1. It's periodic mod 4m minus 2, and it's odd, making this thing a false theta function. Okay, so we can talk about its values at roots of unity as radial limits. So here's the following. Here's a classical fact. This gives in fact, the entire asymptotic expansion at any given root of unity. So I'll read this. So C sub f of n is a periodic function with mean value 0 and modulus f. Then as t approaches 0 from above, we have the following asymptotic expansion. So this is the function we'll be interested in. And it has this asymptotic expansion. So these L values are given here. This is a formula. And bk plus 1, bk of x, is the kth Bernoulli polynomial, which I spelled wrong. Okay, so this is the asymptotic expansion. And to get the radial limit, we're just interested in the constant term here. Okay, so there's just a formula for this. This is standard classical asymptotic analysis. And so how do we obtain these values? So we replace q by zeta sub n to the m e to the minus t in our identity, expressing the q series as a false theta function. So that's this. And if you do that, then over here, you have something which looks something like this. So you have e to the minus n squared t and some thing in front. And then you have to verify that it satisfies the conditions of this result. So you have to verify the periodicity and the mean value properties. So I wrote that here, verify the periodicity and the mean value conditions. And then the constant term gives a limiting value. Okay, so that's just a computation, which I omit, but I'll tell you what we get. So C sub m tilde at zeta n to the capital M. So this is a primitive root of unity, odd root of unity, sorry. This is the formula. Okay, so it's just something that you just get. Okay, and then in step 3, we define the truncated series, which, like I said, is just the truncated series. So we just truncate this, forget about the prefactors. And we use the Bailey lemma again, the same way, if you look back in part 1, the same way we did for Hikami's functions. and we get an identity at primitive odd roots of unity. So this truncated function evaluated zeta n to the m is this thing here. Okay, and then all that's left to do is compare this expression here with the expression obtained for the radial limits at roots of unity. And, well, you don't see right away that they're equal, but it's just a short calculation to prove that they are equal. And this gives us theorem. So let zeta n to the m be a primitive odd nth root of unity. Then this radial limit on the left-hand side, c sub m at zeta n to the m, is up to a root of unity equal to the truncated version of the series evaluated at that odd root of unity. Okay, so somehow this is saying these radial limits are just obtained by truncating the series and evaluating. And like I said last time, probably we see no reason why this should be true, but it is true. Okay, so let me give another, or just one more. I'll just state this. I won't go through the argument. So we define a function gamma sub m of q. So this is a q hypergeometric series. We define its truncated version, which is obtained just by truncating. And it turns out this gamma sub m tilde is a false theta function, and we have the following result. Again, we have to use primitive odd nth roots of unity to avoid poles. But the radial limits are obtained by evaluating the truncated series. That's what this theorem says. Okay, and one last one. So we did 4 of these. Well, we did Hikami's conjecture, and then we did 3 more. So this is a lambda, capital lambda sub m, superscript a tilde of q. So it has a constant and a q prefactor. It's a q hypergeometric multisum. It happens to be a false theta function. And so we define its truncated counterpart. It's obtained by truncating. So I said this is a false theta function, and then this is the result. Okay, these radial limits are obtained by evaluating the truncated series at the same root of unity. Okay, this is all just done using Bailey pairs. Well, plus the classical theorem for computing radial limits. But what's amazing is that the Bailey pairs just give you exactly, not quite exactly, but almost just give you this formula for the radial limits right away. Okay, so let me talk about some maybe an unexpected application, one that I really like. So it turns out that in the 4 examples we treated, some of the expressions for the values at roots of unity overlap. So if you look at the truncated series, I'll explain what I mean with an example. If you look at the truncated series and the formulas you get, sometimes they're the same, or at least for certain values of a and m. And this leads to Q-series identities at roots of unity, something that's been interesting me for a number of years now. We tend to look at Q-series and what happens inside the unit disk. We talk about Rogers-Ramanujan identities and such. So these are analytic identities for Q inside the unit disk, but there's also something going on at roots of unity. Okay, so for example, compare these two. Okay, so this is one of the truncated series. This is the phi function. This comes from Hikami's setup, and this is one that Sharma and I looked at. This is a gamma. So I didn't write it down, but I think I can spot it. So if you take little a equals 0, and then m equals 2m minus 2, little m equals 2m minus 2, then this becomes here, this exponent becomes 2m minus 3 squared, which matches this. If little m equals 2m minus 2, then this upper bound becomes this. If m equals 2m minus 2, these chi's end up matching, okay, and the exponent ends up matching here, and the only difference is in the constant. So if I take little m equals 2m minus 2, we're just off by a factor of 2, and this constant's in front. So this is what I mean by the values overlapping. So if we take a equals 0 and m equals 2m minus 2 in the first of these, then we get these strange-looking identities. So for m bigger than or equal to 2 and q a primitive odd capital nth root of unity, this Q series here is equal to 2 times this Q series here. Okay, so these are not Q series identities inside the unit disk, and these don't come from, these are not Rogers-Ramanujan type identities or anything like that. Obviously, this one starts here at 2, and this one starts at 1, if you look at the Q expansion. So, They're certainly not equal inside the unit disk, but they are equal for any primitive nth root, odd nth root of unity. Okay, so those are some big formulas, but let me show you what this looks like in a simple case. For little n equals 2, this reads the following. So sum n equals 0 to capital N minus 1 minus 1 to the n q to the n plus 1 choose 2 is equal to twice sum n equals 0 to capital N minus 1, this thing, minus 1 to the n q to the n squared plus 1, n q squared sub n over minus q sub 2n plus 1.
So this too is valid for root of unity, right?
So it depends on capital N. So here, capital N should be odd, and this is only valid for q equal to the nth root of unity. Yeah, but I find these quite interesting. Okay, it certainly doesn't hold for absolute value of q less than 1. Right, and you can test this for your favorite odd nth root of unity. Perhaps it's capital N equals 1, in which case the left-hand side just reduces to 1. The right-hand side just has one term, which is 1 over 1 plus q. But if q is a first root of unity, then q is 1. So 1 over 1 plus q is equal to 1/2 times 2 is equal to 1. That's a baby example, but this works for any capital N, odd. Okay, another example, I won't give you the values that came out at roots of unity, but it turns out that this is true. So if m is bigger than or equal to 2 and a is between 0 and m minus 2, then for q, a primitive odd capital nth root of unity, one has this following family of identities. And again, this is only valid at certain roots of unity. Okay, and when m equals 0, when m equals 2 and a equals 0, this is the following. So the left-hand side is just a little double sum, truncated capital N minus 1. The right-hand side is a simple little q series, truncated at capital N minus 1. And these two series are equal when q is primitive capital N root of unity, right? Capital N odd. Okay, so that's something I really like. Again, this is not an identity for absolute value of q less than 1, which you can see right away just by looking at the constant terms. Right, the left-hand side starts at 1, the right-hand side starts at 2. Okay, so that brings me to the end of the second half of my talk. Hopefully it was better than the first half. Some takeaways. So there are a bunch of these, and I want to make a few points here. So if you remember anything from this talk, you should remember the following things. First, there are interesting Q series arising in knot theory. Okay, so everything I considered here arose originally from Hikami looking at Q identities associated to certain torus links. And not only in this talk, but this is something I've been thinking about for a number of years. There are lots of interesting Q series arising in knot theory. For example, you can prove Rogers-Ramanujan type identities by computing knot invariance in two different ways. In fact, you can prove a whole subfamily of the Andrews-Gordon identities by proving colored-Jones polynomials for certain torus knots in two different ways and looking at what are called the tails. And you just get all sorts of Rogers-Ramanujan type identities. I have a paper on Mach-Theta functions coming from quantum invariance associated to 3 manifolds, and we discovered new Mach-Theta functions looking at these. Not just one or two, but whole families of Mach-Theta functions. Okay, so keep this in mind. There are interesting Q series arising in knot theory. The second point I want to make is there are interesting Q multisums with this term. So maybe you're not used to seeing things like this. Hikami constructed his functions using this product of Q binomial coefficients. And this thing actually comes up quite often. So Hikami proved what he calls an Andrews-Gordon variant, so a variant of the Andrews-Gordon identities that contain exactly this product. There's some recent identities of Chern, Lee, Stanton, Zhu, and Yi. Really nice identities inspired by their work on certain algebras, which contain this term. And some very recent work of myself and Kanade. We looked at these and put a lot of this into the framework of Bailey pairs. So that's a story for another day. But there are interesting Q multisums with this term. Okay, so just something philosophical. Sometimes math is easier than it looks. So I talked about this point a bit more in the first part of this talk, and I was saying that Hikami kind of hinted that, well, he did the case A equals zero of his conjecture using Kashayev invariance for torus links, and he didn't see any connection for the general case to any kind of knot theory or quantum invariant, somehow hinting that something really, really substantial was needed to prove the general case. But this wasn't the case at all. If you just strip away all of that and just look at the functions that you're supposed to be looking at, things become really easy. Okay, so this you all knew probably, but just a reminder that Bailey pairs are powerful. So we wanted to prove Hikami's conjecture, and the natural thing to do was to use Bailey pairs. And if you do that, everything just comes out perfectly. This is certainly not the only time in history that using Bailey pairs has made things come out perfectly. The last takeaway is that Q series at roots of unity are worth a look. And so I talked at the end of the second part today about applications at roots of unity. And this is something that I'm also interested in, Q series at roots of unity. So you obtain sometimes things, I didn't talk about these in the talk today, called quantum modular forms. So these are modular forms that are not defined or not necessarily defined inside a unit disk, but they have some modularity property as functions at roots of unity. And you can also look at just Q series without thinking of modular forms. And this is what I call quantum Q series identities. I wrote a paper on this. These come up from in all kinds of different areas, coming from knot theory, just coming from applying Bailey pairs like we did today, or applying a classical Q epigeometric series identities. You can find lots of Q series identities at roots of unity. And I find these quite interesting. And again, that's a story for another day. Okay, so the final takeaway is don't give your online talk during a snowstorm. Again, I have no hard evidence that this was actually the cause of the outage, but I have my suspicions. Okay, so I hope the second part of the talk was okay and it clarifies some points from the first part of the talk, and I say thank you.
Thank you, Jeremy, for a very nice talk. Are there any questions? So I have one question. So Hikami started with that torus link m comma 2m or something, I
2
guess.
comma 2m.
2 comma 2.
Yeah.
So are there some other torus links which one could study and then accordingly get some more identities of this type?
So there are other torus links you can study. My experience with torus knots, which are analogous to torus links, is that if you don't have the first component equal to 2, things get a lot harder really quickly. Okay, so the torus knots are 2 comma 2m plus 1, and the torus links are 2 comma 2m. So these are just indices for families of knots. So that kind of covers everything in the second component, and you have 2 in the first component. And when you move up to 3, things get a lot harder quickly, as I said. So things are known for like 3 comma 2 to the t in the case of torus knots, 2 to the power of t, but not for much more. So torus links, yeah, maybe you could look at 3 comma 3 to the t or something. I don't know, but that gets that's too hard for me.
And another thing is that identity which related that function with the truncated one, just having a power of root of unity in front.
Yeah.
This is true for every capital N, which is a nice thing. Because of course, if you take that truncated one on the bottom of the left-hand side and then let n tends to infinity, the left-hand side becomes 1, the right-hand side should also become 1 because it's the root of unities to some really large power. But it is true for every capital N, which is kind of nice.
Yeah. Yeah, I like those identities.
Okay, any other questions? If not, let's thank Jeremy again for coming again and giving a talk, part 2 of his talk.
Yeah, thank
And
you for coming back.